Hi, thanks for watching our video. My name is Daniel from Wensveen.
And I'm Omar Ali.
And we are two students at the University of Bath studying integrated mechanical and electrical engineering.
And today we're going to show you the electronic tuner we designed using Matlab for our first year RMS prototype project. Before we get to know how we made our prototype, it is important to understand what an electronic tuner is.
Electronic tuners are used in music to tune instruments to a desired pitch.
They do this by measuring the frequency of the sound that the instrument is producing and comparing it to the desired pitch frequency.
The information of how far or how close the measured frequency is to the desired frequency is shown to the user via display, who can then retune the instrument and repeat the process until the instrument is accurately tuned. Although we didn't have any previous experience with Matlab, by researching and using Google, we managed to get a code working in the end.
We needed to know a few things about the sound to make an effective tuner.
These were the frequency, pitch, and accuracy of the measured frequency in relation to the note it needs to be tuned to.
And here's how it was done.
Here's a snippet of our code that shows how we process the audio signal to find its frequency.
Using the Fourier transform, we took the recording of a sound and converted it from its time domain into its frequency domain.
And to find the fundamental frequency or sound that we can hear, we assume that it will have the highest amplitude in the frequency spectrum shown.
Knowing this, processing is done, and Matlab returns a fundamental frequency value.
In this way, the frequency of the sound was found.
After being able to return the frequency, we had to find out its pitch. For example, as seen in the table, a sound of 32.7 Hz is known as a C1.
The frequency for each step in pitch was found, and next, we had to decide the measured frequency ranges. This was calculated on Excel, as can be seen. In total, we programmed our tuner to be able to tune pitches from C1 all the way to C7.
All this information was useful as it allowed us to display the pitch that was trying to be tuned on the GUI.
So, the GUI had to be made so that the user can interact with the program. As can be seen in this picture, a toggle button was used to start and stop the tuner program.
5 O's were programmed to pop up during tuning and gave information about accuracy. O's to the left meant the frequency of the sound was still too low. O's to the right meant the frequency was too high. The middle O only activated when the frequency was accurate enough.
Additionally, the colors of the O's also helped to display accuracy. A red O meant that the frequency was within plus or minus 30 to 50% of the range away from the desired value. Yellow O's showed the frequency was within 10 to 30%, and lastly, a sound would only give a green O if it was within plus or minus 10% of the range away from the desired frequency. So now we'll be showing the electronic tuner in action, and to do this we'll be using an online tone generator or frequency generator to play a pitch of an A4. You can click that here and you can see that it'll become 440 Hz. So we'll play the sound and then start the program using the toggle button. And it can be seen that the frequency measured is 439, which is indeed very close to the online tone generator's frequency. And this accuracy is further displayed by the green circle over here. And what we can do is that if we increase the sound generator frequency, the measured frequency will increase, and also it'll correspond to the accuracy circles. So we can increase it and the circles will go up until you'll eventually even reach the next pitch. And the same happens in a reverse way when we go downwards with the frequency.
Another thing we considered was frequencies that were too high to be measured by our device. We have the device set up to display pitch too high when this occurs. This can be seen here.
And lastly, to improve the user experience and fluidity of our program, we made it so that the screen always resets to neutral values when the tuner is toggled off. This is displayed here. When a tone is generated and the program is turned on, while it's measuring, we can turn it off and neutral values will be shown.
In conclusion, our electronic tuner seems to perform its task very effectively and is capable of measuring frequencies to a high degree of accuracy.
The GUI is easy to use and helps display the pitch, frequency, and accuracy of the measured tone.
One problem with our tuner is that it requires an environment with low background noise, due to the fact that it uses a microphone to record the measured frequency.
Additionally, the microphone needs to be of decent recording quality and must not distort.
Also, our program assumes the fundamental frequency of the sound note is the highest amplitude point on the frequency domain graph.
However, this is not always the case, as different instruments have different harmonic patterns. But despite this, in ideal conditions, it has been shown that our tuner performs well, and we even have extra content available of us using our tuner to tune a guitar and displaying how well it performs. Thank you all for watching.
It's all